Actually, I was asked if I would talk about applied dynamics. And it seemed to me that, you see, in the mathematical community, not very many people are dynamicists, whereas in the physics and engineering communities, virtually everybody is a dynamicist of some kind. So applied dynamics is almost all the work done in dynamics. I thought that was a little bit awesome. So then I decided, well, okay, I will talk on topology. Okay, let me just measure the audience here. Who knows what a continuum is? Oh, pretty good. Pretty good. What?
Everyone learned yesterday.
Everybody learned yesterday. Okay, what's a continuum? This is pop quiz.
I came late.
So a continuum is a compact connected set.
Not a point. Metric.
Not a point? Why not a point? Why not? And so in my lecture, I think I will waffle back and forth between applied dynamics and topology. The topology will really be continuum theory in dynamics. I guess many of us have split personalities. If they tell me to do applied dynamics, I do topology. If they tell me to do topology, I do applied dynamics. And perhaps it comes out looking pretty similar. I guess I would like to begin by talking about I could show you a picture. How about that, a picture? And then you have to guess which lecture this picture is from. It's a trick question here. Here. Is that well focused? Let's make it. What?
Charlie Jackson Pollock.
Here's some more varieties. These are really for purposes of focusing, I guess. It's a trick question because this is from neither lecture. This is from a fellow across Long Island Sound. Srinivasan is an engineer who studies fluids, and he takes pulses of ink and he shoots them into other fluids, and here he's basically emphasized the boundaries between these two fluids. So if one wants to study the topology of this, and I would like to describe the topology, you can see that the difference between topology and applied math gets blurred a bit. Srinivasan is one engineer who is very mathematical, a lot of creative mathematical ideas. Pardon? They are computer-enhanced images of fluids, actual fluids, where you shoot it in and then you sweep a laser beam across the fluid. That gives you a two-dimensional image. And then you take a picture of it and then you computer-enhance the gradients in light. One of the things about mathematics is that and dynamics is that it's gone through a history of talking about very complicated shapes only to find that these shapes are in fact common. And of course we all know that. It happens time and time again. Okay, let me try one on you here. Here I've drawn a picture of a solenoid, beginning of a solenoid. You don't believe that, huh? You take a map and then What?
Good thing Bob Williams.
No, he synthesizes it. Yes, of course.
Most of us can read about the ancient history, but Bob can remember it. How about that? So you take a solid torus and you map it into itself as shown, and then you iterate the map, and you get a sequence of more and more wrapped solid tori, and then you intersect the whole thing. That's a solenoid, right? So one question which a number of people have looked at is there a flow on the solid torus with an invariant solenoid? Now, if you're talking about a reasonably smooth torus, you can show that because of the wrapping, and if you make some assumptions on the uniformity of the sizes of the annuli as they go down, you can show there is no flow that's C3 or something like that. So one might suspect, incorrectly, that the answer is no. If you take flows in 3 dimensions, nature is somewhat perverse in that if you take a periodic orbit, which then period doubles, and then period doubles again, and you go through an infinite cascade of period doublings, at the limiting value, which is the Feigenbaum value, so to speak, you have a flow in America we call it the Feigenbaum value.
France too.
France too. We call copying machines Xerox machines, you see. That's for identified, but they aren't all Xerox machines, but in any case. So when you have this infinite cascade of period doublings, at the end you necessarily have a flow, everything's sweeping around, and you have a solenoid, which is the limit of all these periodic orbits. So while you might go and prove, hopefully your paper doesn't get accepted, that you can't have these things because you've assumed too much uniformity. In the case of the solenoid, the sizes of the different loops are rather non-uniform, just automatically. And these are for analytic flows, real analytic flows. So the point is that when you think of something and can even prove something doesn't occur, lo and behold, it goes ahead and occurs all over the place. Virtually all chaotic flows in 3 dimensions will have period doubling sequences at some point, and we'll have these things. So something which occurs almost everywhere and has a strange topology seems to us that it shouldn't exist because of all this twisting. So this is just an example then of how peculiar things in fact turn out to be very common. I would like to tell you what a indecomposable continuum is. A simple idea. Indecomposable continuum. Basically, you have a set. I'm going to be interested in sets in the plane here in any case, so I can draw a picture of it. And so we have some kind of a set, and it has, if it has the following, it's a connected set, it's a continuum, such that if you take any cookie cutter shape and chop into it, of course a cookie cutter could miss the continuum, that doesn't count, or it could include the whole continuum, but if it cuts the continuum, then it cuts it into an infinite number of pieces, an uncountable number of components. Inside this, you have an uncountable number of components. So that's an indecomposable continuum. And that indecomposable continuum is, for example, the kind of thing you're seeing in the fluids. If I can get the lights on up here, I want to show you, again, this question of mixing topology and applied dynamics. Here I have brought a double pendulum. This is built with the absolutely best roller skate bearings you can buy. And this is a more or less chaotic process. And you should stand up if you're in the back, otherwise you won't see it. Now this is, when I was a graduate student, people said the way you analyze something like a double pendulum is you look at the modes of oscillation, and this is one mode of oscillation where they go in opposite directions. This is for small amplitude oscillations, and the other mode is where they both go in the same directions together. That's a little bit rickety one, but it's a combination. Then all motions of this small amplitude would be combinations of this. And if you were a graduate student in math or physics or engineering, basically this is all you could say about this kind of a thing. Whereas in fact, if you do this, you also have to keep the students away because they might give it a flip like this, and you quickly see motions which cannot be thought of as combinations of those two modes. Okay. What you're seeing here is sensitivity to initial data. Fortunately, there's some friction here, so it will stop, so it's not really chaotic. But you are seeing sensitivity to initial data. Your eyes are seeing patterns. Your eyes are seeing the patterns and then the pattern changes. And it's this changing set of patterns is, one fellow who's a dancer told me it looks like it's having fun. Usually I try to get these with more friction in them so that they stop after a while, but I try to get people to guess when is it going to, the lower one, when is the lower one going to flip last? Raise your hand if you think it's quit. So that's predictability. You're seeing lack of predictability. You think you see something's happening you can't predict. Ah, finally. Finally. They don't think it's going to go again. So now the question is, since this is a topology lecture, did you see the topology in that? There must be some in there, right? So the co-producer of this is going to show us a video of a dynamical system, a strange attractor. You can't see the topology here, but it's here. And this happens to be in a Kata map. It's a map in the plane. Is it stopped? We've got to get it started somehow. Lights out would be good, I guess. You can see it better. What we decided to do is take an attractor such as you can easily produce on your computer screen in 30 seconds and zoom in on it. Zooming in on it means that it's actually far more difficult to compute. What you're seeing here is different densities, the probability measure on this, and the yellow represents relatively high density regions compared with the low density regions. And I just thought you might want to see what one of these things looks like if you actually zoom in on it. Computationally, this is quite difficult. What you're seeing is an indecomposable continuum. At any given point, the stuff that's in the screen is an infinite number of, uncountable number of components, if you just chop it off at the screen. But of course, the whole thing is connected. So you're seeing an indecomposable continuum, and you're continuing to see new pictures with new places of chopping it. And so it's also interesting, as you zoom in, you can see the low density regions continue to persist. Now that last couple frames took something like a week on the computer because we zoomed in so far. So this is just another way of showing you what an indecomposable continuum is. If we could stop that and pop it out. So indecomposable continua are also things which occur everywhere, and Marcy Barge has a theorem. He's actually got some technical hypotheses, but perhaps this hypothesis gets around it. Basically what he's saying is, if you take a periodic orbit and you look at its unstable manifolds and its stable manifolds, and if there's a homoclinic point, then there exists an indecomposable continuum, which is invariant under tau. So, happens all the time. Indecomposable continua happen all the time. Next step in worseness. Okay, this thing is a indecomposable continuum. Let me just ask you, suppose you were to take one component of this thing and it looks like this. What does it look like? Well, assuming you take a reasonable slice, what they've all looked like is nice curves. In the examples we've seen. So that's not necessarily the case. A number of outstanding topologists spent good parts of their careers studying a case where the situation is worse. One of the ideas is to take the worst conceivable things you can imagine and show that they occur every day. Sometimes I give talks to physicists, and I address the question of what's new and interesting in dynamics. And I tell them the answer is nothing. Because all the ideas in dynamics that people suddenly encountered around 1980 turned out to have been very old ideas, perhaps 80 years old. And these ideas really weren't new. They were interesting. But probably when they were first discovered, they weren't interesting to very many people. The interest came later as the ideas matured. And how many people know what a hereditarily indecomposable continuum is? Got one, two. Okay. Okay, now, if whenever you cut this out, you take a component, that component is an indecomposable continuum. Hard to picture. So, the term here is hereditarily indecomposable continuum. So, if whenever you take a component, it's indecomposable, and then whenever you slice this component and look at its components, which will be uncountably many, and you take one of those, it's indecomposable, and so on all the way down. It's a hereditarily indecomposable continuum. Actually, you can state this in just two steps. You don't have to go all the way down, but it follows that it goes all the way down. So that's a hereditarily indecomposable continuum, and you'll note that if at any point it contained a continuous curve, then it wouldn't be hereditarily indecomposable because you'd be able to pick out one of these components. So this is pretty bad. You can't get, given any 2 points, you cannot connect them with a continuous curve. Forget smoothness. I mean, Weierstrass number differentiable curves, that's a continuous curve. So we need things that are much more irregular than that. Do things like that occur in dynamical systems? Yes. Examples of dynamical systems with pseudo-circle attractors were constructed by a number of people. These examples that they've constructed are somewhat fragile. When I was talking about these other things like solenoids, I was trying to emphasize that they occur virtually everywhere. If you've got a system depending on a parameter, or it's a chaotic system, you can expect to see them in 3 dimensions, a flow. You can't avoid it. Whereas here, these results are really only saying that they exist. Pseudo-circles, I will simply leave, they are circle-like things which are in decomposable continuum. Now, how is that for a contradiction in terms? Okay, so basically they are hereditarily indecomposable continuum. So let's say that examples of dynamical systems with hereditarily indecomposable attractors were shown. These things are basically, they can be approximated by circles. Given any epsilon neighborhood, you can run a circle through it and come close to it. And in higher dimensions, one just talks about hereditarily indecomposable continua. There are many different ones which are not homeomorphic to each other. So I wanted to tell you about a procedure for that Judy Kennedy and I have found for actually showing that these things exist. It'll take a few words. First of all, one of the shocks that came to some people, in fact, Steve Smale talks about how he tried to look at dynamical systems which were very tame at first, and then he found that there were Cantor sets of things, infinitely many periodic orbits. So let's ask, how do Cantor sets occur? We know how Cantor sets occur, but I will persist. I want to draw you a picture of how a Cantor set would occur to show you what the next stage would be. Suppose, for example, we took a square and we map it into a Smale horseshoe. Then, assuming the sides line up and everything, we get an invariant Cantor set lying in there. We all know this. Now, suppose we take this planar object and put it in 3 dimensions and cross this with a circle. So, in particular, let me not quite cross it with a circle here, but just try to show you what we're talking about here. I'm getting in trouble here, but okay, you get the idea here. Okay, so what I have here, then, what I would expect to get is, instead of a Cantor set of points, I would expect to get a Cantor set of circles. So let me try this again. Over here, in my horseshoe, you see I have 2 things like so, and here's a piece and here's a piece. Now, if you cross that with a circle, you wind up with each piece being like a washer. And there are 2 of these. There are different ways of constructing, of getting invariant sets, and this is the simplest version. But one way of getting a Cantor set is a slightly different thing. If we look at maps instead of homeomorphisms, we could take 2 squares, and we take the left square, and it maps onto a bigger square, and the right square maps onto a bigger square. So instead of being squeezing and expanding. This is just purely expanding. So in any case, of course, in here we would get two Cantor sets. And given any sequence of lefts and rights, we would have a point that follows that sequence. And when you look at these washers, strictly speaking, the washers we construct don't come quite from the horseshoe construction. They come more from this expansive construction. The idea basically is that you have one kind of a map holding here and one kind of a map here, and each one expands over to the whole thing. The kinds of maps that we wind up with are, in fact, really pretty simple. But by constructing an appropriate map here and an appropriate map here, we are able to get that these circles, remember you've got a Cantor set of circles, the circles become distorted. And most of the circles are pseudocircles. Now, of course, in a Cantor set, each point is not invariant. The invariant set is a collection of these. And so our pseudocircles are not invariant. The pseudocircles are mapped to pseudocircles. The invariant set is a collection, a Cantor set of circle-like things, almost all of which, in the topological generic sense, are hereditarily indecomposable. The maps we use are very simple maps, and it turns out these maps are so nice that this structure persists under small perturbations. In other words, our construction is so simple that we wind up with an invariant set, most of whose components are indecomposable continua, and this holds for an open set of diffeomorphisms. This is often a good criterion as to what is something you are likely to see. I would also like you to think that while we have a particular construction, the elements of this construction are so simple that one would expect to see it in other renditions. Let me tell you what our theorem says. On any 7 manifold, there is an open set of maps. Actually, well, here I should say, as I say below, this should be diffeomorphisms, or I should say on any 3 manifold, there is an open set of maps. So take your choice. Maps or 3.
Is it C1 topology or
These are C-infinity maps, real analytic maps. CN.
In what topology?
Pardon?
Open in what topology?
C1 or CN. And we have this kind of phenomena. Now, small perturbations produce these objects. The objects, it is actually not structurally stable, as far as we can tell. We suspect it's not structurally stable. As you perturb it, you destroy some of the pseudocircles, and maybe you create new ones, and so they aren't exactly the same. But the structure I'm talking about persists under perturbations. Now, here it's 7 dimensions. Does that mean you will never see it? Well, we strongly suspect that this kind of thing will occur in much lower dimension than our construction is valid for, just as I was emphasizing with the solenoids that one thinks that something isn't going to happen. It's even worse, and it still happens, and it happens everywhere. So we think that this is probably a common kind of phenomena. The question we're interested in here is how bad is the topology of invariant sets? Here we don't have an attractor, but we do have an isolated invariant set. I'm not going to go on and tell you more about that. I'd like to diverge at this point and instead talk about other strange things that can be seen in dynamical systems of weird topology.
Pseudo-circle vents, maybe during the sun.
Yes, yeah. It's a residual set of the circle-like things. Right.
This map which produces that?
Well, I mean, I got 7 dimensions to work with. And I'm only showing you 2 of the dimensions.
Maps, it's 3.
What?
Oh, so
Right. Okay, you're asking here. The basic idea is if I can choose a sequence of maps, okay, left, right, right, whatever, then I can, then the invariant set turns out to be a pseudo-circle. Now, I can actually do this in 2 dimensions. I can choose 2 maps in the plane. So if I choose the right sequence, or almost any sequence of them, and alternate them, I get a pseudo-circle. Okay? And I will tell you what these maps are. Okay, so now we're down to the plane. Of course, to build this into a dynamical system in the right way, I need the Cantor set structure so I can choose left and right at sequence. But again, so here's an alternate view to answer your question. Suppose I take 2 nice maps, and I'm going to show you what the inverse of the map is. One map is, my coordinates would be theta and y, so it's actually on an annulus. Theta goes to 2 theta, mod 2 pi, and y goes to 2y. That's one of my maps. Okay? And actually, if I show you the inverse of the map, here is a unit square, and I look at the inverse of this, and this will have lots of inverses because of the theta goes to 2 theta. So if I take the 5th iterate, I'll have 32 little boxes. So that's one of the maps. The other map, I want to show you what the inverse is. It's again on an annulus, and its inverse takes the annulus onto this kind of a thing. Now, if you look at the force-damped pendulum, you'll see maps like this. You'll see maps like this. Basically, you've got some kind of a shear going on. You take these 2 maps. Again, I'm showing you the inverses, basically. But take almost any sequence of them, and you ask what set of points remains bounded, and it'll be a pseudo-circle. Okay? So you can see that that kind of construction is pretty perturbable and pretty likely to occur in addition. So in one region of the space it's behaving like one map, and the other side of the region of the space is behaving like the other map, and your horseshoe structure is causing you to weave back and forth between these 2 sets. So that's what your extra dimensions are doing. They're forcing you to take some kind of a sequence of points to go back and forth between these 2. Okay, let's go back to what Euclid knew about topology in the plane. And you take a region, you take another region, and maybe everything outside. Here you've got 4 regions. Well, 3 regions is good enough. So I've got 3 regions, and what I mean by a region is a disk-like thing. That is an open disk. This is an open disk. as are the other regions. And I could ask you, what does the boundary, the common boundary of all three disks look like? And so, if Euclid was willing to play this game, he'd say, well, here's a point, and maybe somewhere else there's a point. Actually, if this doesn't quite touch here and we swing it around like so, here's another point, which is in the common point, common points of these two regions. And so a point which is common to at least three disk-like regions is we call a Wada point. And Judy Kennedy and I named these after Wada, lakes of Wada, which were unknown to Euclid. Actually, not much in mathematics was known before Archimedes. Nonetheless, the goal is to Wada constructed three regions such that every boundary point was on the boundary of all three regions. And if you go back and read the construction in Hocking and Young, you will be convinced that such things will never occur in reality, depending on your concept of reality. If you're a topologist, they occur everywhere. The construction is so bizarre that only politicians could create it. And if you look at gerrymandered regions on the boundary, you could well imagine a political region which had these properties. But aside from that, the point I'm making here is that these Wada regions do in fact occur. Here is an intriguing picture. This is a force-damped pendulum, x double dot plus x dot. X is an angle and it's taken mod 2 pi plus sine of x. Here we've chosen to do 1.66 cosine of t. And there are three, so we're looking at a Poincare return map. There are three periodic orbits, which if you look at a Poincare return map, they're fixed points. And these three fixed points, one is in the white region, one is in the black region, one is in the gray. And what these regions are the basins of those fixed points. So everything in the white region is attracted to the fixed point. Everything in the black region is attracted to the fixed point over here, and the same with the gray. Now, it follows that these are topological, open topological disks. Homework problem. And what you seem to be seeing here, seeing is not necessarily believing, is it? What you seem to be seeing here is that every boundary point is on the boundary of all three regions. So we study the pendulum not because we love pendulums, but because no one could claim that we have rigged up this set of equations. And if you look at this, instead of taking mod 2 pi, then you'll have infinitely many attractors, because translates by 2 pi of every attractor becomes an attractor. And they seem to be equally bad. So, again, Wada points are points that are on the boundary of at least 3 regions. And regions are simply connected and are either connected or have finitely many components. In some cases, your basin, your attractor would be a period 2 point, then your basin would be 2 topological disks, and you'd map from one to the other. They'd map back and forth.
Excuse me, is this proved to be one of these Wada regions here? Or is it just
Let me go on. Okay? That's a touchy point. Let me show you some other pictures where one would like to prove these things. This is from basically a Henon map. And you have the set of points going to infinity, and you have 2 bounded attractors, periodic attractors. And these 3 basins seem to be meshed in just this way. Now, to help you analyze this, let me say that there is a fixed point of some interest, which is right about here on the edge. And its stable manifold looks like this. Helps you organize. Its unstable manifold I seem to be lying. That's a slightly different map. There are 2 cases. One is where you have a constant of 0.70, one the other we have a constant of 0.70. Again, here the unstable manifold of this looks somewhat like this. A blow-up of this region up here looks like so. Now this is with the 0.71 here. With the 0.70, you get the interesting construction. What you observe here is that the gray region out here is a Wada boundary. It's got the properties that given any point, the white and black regions come arbitrarily close to it. But the boundary between the black and white regions is nice and smooth. So here is a theorem on this, that the again, I'm often see here, your basin is actually the black is 2 connected sets, each of which is connected. So whether you consider it to be an open disk or a couple open disks just depends on the example. But Judy and I proved the following theorem, that a basin is a set of points attracted to an attractor. That's a trick definition from some points of view. If you have something like a Henon attractor, you can say, well, what's a Henon attractor? Do you have an attractor? All kinds of questions like that come up. But suppose you have an attractor which attracts an open set. Let P be a periodic point, and such as that point on the boundary we're talking about over here, or some other point anywhere in there. There are infinitely many periodic orbits. Let P be a periodic point such that the unstable manifold of P enters the basins BI greater than or equal to 3. The stable manifold, and that's a short calculation. You just compute a piece of the unstable manifold until it enters a couple of the basins. No problem at all. The stable manifold of P is dense in the boundaries of B1, choose a particular basin to speak of, then each point on the boundary of B1 is in the boundary of BI for all I equals 1, 2, 3, etc. So one of the critical hypotheses here is that the stable manifold is dense in the boundary. And if you take a standard example such as a pendulum, you can make pictures, and it looks plausible that this is satisfied, but it's very unconvincing. Now, we were able to construct examples using this theorem directly. Just pick a periodic orbit, and the hypotheses can be verified. But that's very different from a case in which it's easy to verify the hypotheses. So this doesn't tell you how to verify the hypotheses very well. It's somewhat unsatisfactory, and I would like to show that with some intelligent choices, actually, this can become quite verifiable. So this is this mix. Here is a strange topology, and can you turn it into applied mathematics? And in the examples we construct, the examples would not be a natural example. There is a story of the Henan attractor paper. Henan submitted a paper to a journal, and it contained no theorems. And so it wasn't mathematics. And I'm sure the physicists said, well, those aren't physical equations. They don't contain any physics, and therefore everybody would agree it shouldn't be published. But Ruel was the editor, and he did publish it. But despite the great gap of communications between mathematicians and physicists, what's an example for a mathematician is something you can get your hands on and prove things. But what's an example for the physicist is something which occurs more naturally in the domain of physics. And so the question is, are there examples? This satisfies the example hypothesis criterion of the mathematician, but not of the physicist. Yet we show you these pictures. These pictures would be quite acceptable nowadays to a physicist without being rigorous. So the idea is to try to demonstrate this not just for artificially constructed mathematical examples, but to go beyond that. Could you put in the other video? I'm going to return to this kind of a picture. What? Yeah, go ahead and give it. And what I'm showing you a case actually where there are 4 basins, but think of the basins are color-coded, and we're looking at the force-damped pendulum once again, and this is simply a computer-generated zoom on the boundary, so you can see what's going on, or see what you think you see, or see what the computer produces. There are going to be 4 periodic attractors, and so the points which go to one of them we're going to call are yellow, and the points which go to one of them we're going to call green. You can identify yellow and green for practical purposes. And so these are the points which go to the yellow attractor, and these are the ones which go to the green attractor. And this is a periodic orbit which rocks back and forth for the pendulum and doesn't flip overhead. The blue pendulum, the blue corresponds to points which this periodic orbit which flips like so, and the red attractor is ones which go in the opposite direction. Now this is on a cylinder because we're taking it mod 2 pi, the angle mod 2 pi. Vertically we're plotting velocity, angular velocity, and so you get this kind of picture. You're looking at 3 or 4 topological disks, depending on how you count them. And as you zoom in, you will see a great deal of sensitivity to initial data. If you were to put this on a PC and you run it, you wind up simply with one of the 4 attracting periodic orbits. Whereas, if you try to predict, I mean, what could be more important than knowing which attractor you go to. You want to predict the long-term behavior. If you don't know which attractor you're going to go to, you're in trouble. And here, the boundary, while it's measure 0, does seem to be pretty big in some senses. That if you're within epsilon of the boundary, an epsilon neighborhood of the boundary is a pretty big set. We've chosen this case actually partly because the boundary is so thin. There are cases where it is far worse. So sensitivity to initial data is what you're seeing here, that you're seeing that sensitivity to the long-term behavior is being exhibited here. And as we continue to zoom in, you will see that while somewhere in the middle of the screen we're zooming in, that while you seem to see, due to the finite resolution of the picture, you seem to see a region which is perhaps all blue. As we continue to zoom in further, all 4 colors keep appearing. This particular boundary point was chosen to be on the center line of the screen. We didn't choose it very carefully. One of the things you will observe is that the lines seem to all straighten out. That may be an artifact, the fact that we haven't searched it very completely. I think if you looked in other places, you might find, in fact, there's a lot of kinking. You just can't see it in this particular picture. This is not, the boundary is not hyperbolic as far as we can tell. So as you zoom in, you continue to see this ever more complicated structure. What we're showing you here is 220 frames of a video. Each one is made on a computer. Each one is rather time-consuming, so each one has to be made individually. Here, each successive zoom-in is no more harder to make than the original one. When I was showing you originally a zoom-in on an attractor, each one became successively more difficult to make. So this goes on and on and on. And there's nothing particular about the particular boundary point that we're zooming in on. Now keep in mind that if I had picked a red point to zoom in on, soon the screen would be filled with red. So we are looking at boundary points. We're looking at things of measure 0. But in this picture, it appears that almost everything is on the boundary. Why don't you kill that? So the challenge is to apply this theorem with Judy to things like this picture. How would you go about applying it to this picture? Keep in mind, we do not want to produce a 100-page proof of something which is impenetrable, and then if you change the parameters, you don't know anything. But the hint here as to how to proceed comes from the following idea. If you have a periodic point, you can imagine a basin of attraction over here, and if you draw a curve in the basin, the first point you hit is called an accessible point. Now imagine the boundary as being a Cantor set of lines, simplistically, so that almost none of the points of the boundary would be the first points hit, but in any case, the first point hit by an accessing curve is called an accessible point. And I want to talk about the case where you have a periodic point that is accessible from the basin. I'm interested in dissipative dynamical system. That means area decreasing, maps in the plane. And every case we've ever seen has the property that there's always an accessible periodic orbit. Now, one way to get an accessing curve is to look at the unstable manifold, the half of it that goes towards the attractor, and that half that goes to the attractor will be an accessing curve. If you have a Cantor set type of boundary or something like this, you have any kind of a boundary, take a point in the boundary. So you take a point in the boundary, you take a point in the basin within epsilon, and you draw the straight line from here to here. Bingo, you will hit an accessible point. So this is simply a way of saying that there is an accessible point within epsilon of any boundary point. So the accessible points are dense in the boundary. And Kathy Alligood and I proved the theorem. We had to assume some niceness at infinity, some properties which are easily satisfied by the force-damped pendulum. And we were able to prove that if, let's say, B1 is a basin, imagine a basin of a fixed point for simplicity here, but a disk-like set, a basin of a fixed point will be an open disk. And assume P is an accessible point at period K, then every accessible point will be on the stable manifold of a period K point. Okay? Now, I'm not saying this period K point is the only accessible periodic orbit, but every periodic orbit that's accessible will also have the same period. Basically, you have something like a topological nice disk, and it's rotating. It's somewhat like that. Not quite a rotation, though. Basically, you have a structure which is something like this. You have, topologically speaking, it looks something like this. And then you'd have a couple period 2 points. For example, this point maps to here. It rotates 180 degrees. All the other accessible points are on the stable manifolds of these period 2 orbits. This is very simplistic. This isn't like what I drew, and yet that's what the theorem says. The theorem says that all the accessible points are on the stable manifolds of the period K orbits. So if you find one accessible periodic orbit, say it's period 2, then you know that every accessible point is on the stable manifold. Now, why is that useful? Suppose it was the only period K orbit. Then you know that its stable manifold is automatically dense in the boundary. Ah, that's the point. The stable manifold is dense in the boundary. Therefore, this apparently unbelievable hypothesis becomes trivially satisfied. There are other questions here. Let me just finish up by trying to make it more provable. There are other questions as to what an attractor is. If you have to tell what an attractor is, you're dead in the water for trying to do anything rigorous other than for talking about attracting periodic orbits. So instead, we came up, Lenny Noosa and I came up with an idea of talking about a region like so, which was a trapping region, consisting of pieces of stable and unstable manifolds. Okay? And this region is mapped into itself. That's why it's a trapping region. Its boundary are the stable and unstable manifolds. And we say that everything that falls into this trapping region is in the basin. So we define basins instead in terms of trapping regions. This becomes much more, puts a much better foundation on this thing. Furthermore, when you look at basins like this, lo and behold, you can prove there are no other accessible periodic orbits. So in a stroke, you no longer have to find out, you automatically know that the periodic orbits, this particular periodic orbit has a stable manifold that's dense in the boundary. I should say I've been telling people for a couple of years that in 2 months Springer's going to publish my book. No laughs on that. For a couple of years I've been telling people. Well, in 2 months Springer's going to publish a book with Lenny Nusa, which is a dynamics program in which you can find accessible periodic orbits automatically and carry out many of these computations. They are, however, to answer the trick question over here, you find a periodic orbit, you haven't proved rigorously that it exists, you just see it. You calculate a stable manifold. These are very easily to compute. You haven't proved that it's computed to the last epsilon. There are all kinds of things you haven't really computed, but you can verify this construction within 16 digits, shall we say. So, I'll quit here.
Any questions? Anyone else want to be insulted?
Using x double prime plus 0.1 x prime
Yes.
sine x equals cosine p.
Right.
With the x actually not folded around, going all the
Right.
way from minus infinity to plus infinity. And my impression is that in that case, the basins do not have any periodic points, any accessible periodic points in their boundary.
You haven't used my program. You're probably using John Guckenheimer's program.
No, I'm definitely using Ben Hinkle's program.
Well,
You ought to be.
now you see, actually it's fairly easy to find the accessible periodic orbits. So your impression, yes, these things can be hard to use if you have bad tools.
You're saying that they exist?
The accessible periodic orbits, we've gone through dozens of
They
examples.
exist in all your examples.
Yeah, they exist in all the examples.
We get together and
Put you.
Hubbard's parameters in your program.
Yeah.
Do I have a copy of the program with me? Maybe. Now all we need is a PC or workstation. Works on almost everything except the Macintosh. $49.95 unless...
Well, let's see if we can find these points. We're not going to buy it if they can't find these accessible periodic points.
Demo right now. Real-time demo. Let's go.
Well, the 6 inch right next door, we can get on that.
Can we download this on the internet? So we can do a test, and we'll tell people later on today whether they should buy your program or not.
Let's thank the speaker again.